Hello everyone. So today I would like to go through and implement the second half of the if expression. So last time I was able to get the front end part working. This time I would like to get the back end working. So first I'd like an example of what an if expression would look like. So I think I have an example that could work for this. So if we grab Fibonacci here, notice that it has a lot of if-elses. So what if I were to copy this, and instead of saying return here, I would say this. Return if position is less than 5, then return position, else if position is. So as you see, we can just rewrite existing code in terms of this, as this is a much easier way to write. So there. This should be effectively the same. So now if I go and build up this, so we get to say that we want to test the if expression example. Fascinating that it hangs. I know why, though. I think I know why. So if we look in our visitors, all we know at this point that the if expression is an expression. So if we were in, say, the type checking visitor, and we asked to find what an expression would look like, as you can see, the expression would just accept itself. However, since we haven't added the if expression as a potential visitor, we effectively get this infinite loop. So to add the if expression, we can go to our for declaration of nodes, and we will add the if statement, and just above the if statement, we will add the if expression as a node. And now if we build, we should get some build errors. There we go. Undefined reference to Codegen visit this, Codegen printer, and the type checkers visit. Okay, so let's do the easiest one of the three visitors, the printer. And that we can use as a prototype for the other ones. So in the printer, we will put this right next to the if statement, because both are if. Because I think these are sorted in alphabetical order. Or did I not put them in any order? No, these are alphabetical. Okay. Just having to remember my declaration order. And so now we change the if statement to an if expression, which here means that these are all going to be changed. And furthermore, since we know the if expression will never have a null, this is the then case, and this is, if I remember correctly, the else case. And so there, that's the printer. And as you notice, the printer very simply just walks over the nodes and prints each one out. The next thing we will need to do is the type checker. So the type checker, it also is sorted alphabetically. So if I were to find the if statement, there it is, I can roughly make the if expression. And so as we see here, we get to write that the if expression exists, and we get to visit the if expression. And so now we have to get the value, and so you notice we first get the value, effectively get the type of the condition. And if the type is not the same thing as bool, we must check that that's not the case. And then here, we'll have to check that the left-hand side is the same as the right-hand side. So this we need to check. So we need to check that the left-hand side, that the then case type is the same as the else case. Okay. In order to do that, we will first get the then type, which is get value of the if expression, the if expression's then case, passing in this as the context. Yep, there. And so now, the one issue we have here is we have to dereference these. And the reason I'm fine with dereferencing them is that I know that this is always non-null in C++, and the then case will always not be null, which is guaranteed from the abstract syntax tree. And I can also now generate the else type, which will take the else case and generate the same thing. Now we have to check that if one of these two types, now we have to assert that both of these are non-null. Currently, the error checking on the error checking in this stage is not I have not had time to decide on a good error checking methodology, or an error reporting methodology more accurately. So I have resorted to using asserts, and eventually if an error occurs, I will have to write a better error reporting. And finally here, we can say that if the then type does not equal the else type, we can say something like the then and else branches of an if expression must be of the same type. And then we shall assert false, saying that we can progress no further. Now here, because we're in an expression, we do need to return a type, which we do with store result as part of our visitor pattern. And we will store the result that is the then type. Now, it technically doesn't matter at this point whether we store the then type or the else type, because at this point we have confirmed that they are equal, but I would prefer to store the then type. So now that we have this, we can finally do code generation. So to generate the code for this, to generate the IR in particular, we can start with looking at the visit function for if statements. If I remember correctly, here it is. And we jump down here, and we can copy this, and we can paste this above, and we will now say that this, instead of being a statement, is an expression. That is correct. Okay. So now we get to say thing. So now we need to, so when we generate the code for this, we need to first evaluate the condition. And then we get to evaluate which block we're in. However, there is a slight trick here. Because this is an expression, there may be optimizations we can do here. For example, if the condition is a constant value, we can make some interesting optimizations by only generating half the required code. So, for example, if if LOVM can dynamically cast to an LOVM constant and we'll call this the constant condition. If our condition can be cast to that, and our condition does not equal null pointer, we can do something there. Now I'm going to open up a instance of web browser so that I can see LOVM, that I can see the LOVM value tree so that I can remember these things. Let's see, constant. Constant integer is what we want. However, I can just cast to a constant, and then we will probably have to cast down to a constant integer. Can a constant integer tell me whether it's false or true? Get type. Well, we know the type at this point, so get boolean. There may be a way to do this. It turns out it's an AP int. What is this AP int? A number of bits and a value. We've got constructors, we have equality checks, comparison operators, bit values. Okay. What if I were to just do this and get these values out? Which these are constant ints. So we would say get true based on our context, get false based on our context. In fact, we could just say get true and get false. Okay. My apologies there. So if this is a constant, we will then check if so here we will say now that if the condition happens to be get true, so we have constant int that we need to get, and constant int has the true and the false on it. Okay. And so here we now get to get the there. Okay. And so now here, once we have a constant value, we can just store the evaluation, store the result of evaluating so if it's true, we want to evaluate just the then condition. And then we can return. And in the other case, we want to store the evaluation of the false condition. Or no, we don't want to evaluate the condition, we want to store the then branch. And the else branch. Let me just make this and see if that fixes anything. True branch, else branch. One second, I do not remember how I named this. The if expression has has cases, not branches. Okay. It's cases, not branches. Constant condition is not used. So there we can optimize if the constants, if the condition is constant. Now, if the condition is non-constant, but we do have two constants coming up, that could be a different issue. So we get two starting blocks. It's going to be interesting to figure out whether these are constants or not. The then block shall be created. We can probably prove if an expression is constant, but that will be an optimization later. Maybe we should add that as a note in expression nodes. Yeah. In the case that they're, however, in either case, we must continue working. So everything works here up until we get this if expression, which has the then case. We check if we're terminated. Now we know this is always going to be false because we always have to generate the else case. Set up the execution points. However, we can't just accept them. We have to create their values. So we have to say that their value, that the then value is get value based off of this. As we notice that just works. And the else value, which is generated as you would expect from the else case. We set up the blocks and we conditionally break them. Go to conditional branch and we insert termination. If neither of these are terminated, which I think they would not be because they would always, interestingly enough, they would always branch back. Interestingly enough, these would never return because currently their expressions would never return, right? So we have the then block, we set the insertion point, we generate there. Once that generation is done, we will need to branch back to a merging block, which is done here. If they're not terminated, we create the merging block, set the merging block. Okay. So we get to merge the expressions. So to merge the expressions, we will first need to set up a new merge block. So the merge block, which will equal which is a basic block that will be created. Now we'll create it in the same way that we created the other blocks, which is that we pass in our context, an empty string, and the current function we're in. Now, in the case that we are there, now in this case, we'll now tell the IR builder to set an insertion point, to the then block, at which it will then create a jump, create not a conditional branch, but just a branch. The singular argument destination wasn't specified because we need to tell it that we are merging there. And then we can duplicate this logic and put it here where we will say that this is the then block and that this is the else block, and they get merged. And then finally, we can set the IR builder's insertion point to the merge block. And then we have to create a phi node, which, if I remember correctly, there is a create phi, it seems, node. Time to go dig that out. They would be in index, IR builder base, so then we look in IR builder base and we say, looking for the phi node, create the phi. We need the type of the phi node and its number of reserved values, and then we get a phi node back. So the type of the phi node will be the same type as one of the two values. So the then value, we can get its type. And the number of reserved values will be 2. And we preserve the phi node here. And then when we preserve the phi node, we will now say that the phi should, let us see, we should add an incoming value, add incoming with a particular value at the end of the phi list. Okay. So add incoming, which then the incoming value will be the then value. Let's say first we will handle the then value, which will come from the then block, of course. And we can also have values coming from the we can have the else value coming from the else block. And we could simply store the result at the phi node. Store the result at the phi node, right? Now if we build, that should give us something. As you can see, that worked. Now, if I am to build this, we have an error. The basic block in fib does not terminate. Well, we can simply debug. I never expected this to be correct the first time. So, basic block in fib labeled 20 does not have a terminator. Labeled 20 down here has a phi node. This makes sense because this is probably one of the, as you can notice, this here and this here. How do we solve this? Well, this is because we have a nested else if, and a nested else if will mean that this internal block here is effectively the if of another case. Break to label 20. We would have to ensure that both blocks are terminated. I believe so. Thought we ensured that. Let's see. Evaluating the condition, optimize the condition if it's constant. We set some variables up. We have a conditional branch between the two. We then merge the expressions. Technically, the merge, this creating the branch here should just merge them back. Let me see what the if statement did. If these were not terminated, we created a branch back to the merge block. Interesting. Huh. Unless the AST is designed. But it should theoretically do this. Create a branch, create a branch. Let's try something. Let's try, of course, the famous Printf Debugging. So we are merging to 20, which has no predecessors, and we are merging to 22, which has no predecessors. We are merging to 20, and we are merging to 22. This is coming value 21, but it's coming from block 6. Interesting. Why does it have two branches here? This is getting more tricky because this has two branches, and these two branches, and one of them is the conditional, but one of them is not the conditional. Stranger and stranger. Let's see. Let me just think through the logic again. We evaluate the condition. When we evaluate the condition, we can optimize if it's a constant based on what we can optimize based on whether it's a constant, effectively generating only the IR needed for one or the other. In fact, we probably should check that this is a constant integer, unless I think we'll be fine here. We get the start block, and we have the starting block's parent. We then set up the insertion block, then set up a then block to generate the then case. Then block to generate the then case. We set up a else block to generate the else case. We then go back to the start block to generate a conditional branch between the two. We then create a new merge block, which we'll merge to. And we will set the points for the then block to branch to the merge block and a merge block. But if it's not terminated, right, because if it's terminated, maybe that terminated logic is still needed here. We can say something about here. Right, because the else block here would merge. So let's see, if the else block is not terminated and the then block is not terminated, we need to merge the two. So here, create a branch to the merge block. So if the then block is not terminated, we will do this logic. And if the else block is not terminated, we can then merge two, we set the insertion point, we get the phi nodes. That still fails. At least now we don't have these. So wait, that's interesting. Value 4 gets set based on this. So let's see the control flow. So we check if position is 1, is less than or equal to 1. If it is less than or equal to 1, we branch to 3, otherwise we branch to 1. In the branch 3, we set up 4, which is equal to either the value of, either equal to the either 0 here, or the value of 2. This is an OR comparison. That's what's happening here. Okay. then this branches either to 5 or to 6. If it goes to 5, it then immediately branches to 22, which takes in 5 and that. Okay. And in the other case, it branches to 6. It's 6, it branches to 7. Label 20 does not have a terminator. It's very strange. Resolves that. Then we have to branch to 22. The merge block is 20, but only one of its predecessors got merged. Interesting. Okay. Continuing our dive into Printf debugging. The then block. Let's see what happens when we do this. Let me debug this. The then block and the else block, which then merge to 20. Okay. Then we have the then block of 5 and the else block of 6. And they merge to 22. This gets stranger and stranger. We should be leaving the insertion point at the merge block, right? Should maybe be leaving the insertion point at the merge block. We do leave the insertion point at the merge block. We store the value of phi. We expect to continue evaluation from there. But apparently we're in the call stack of a call stack, which can really mess us up. So how do we? Right, because the then block and the else block. So what happens if you have an else? What if you have an else inside of an else if? Okay. So we would generate the else block, and as part of generating the else block, we would generate another if, which would eventually result in merging the two blocks. Merging the two blocks. Ah! The problem is that when we generate the else case, in the else case, or in the then case, we generate extra blocks. And so the then block and the else block aren't what we set them to be initially. They are advanced. So effectively, we have to have some way of getting the current insertion point from the IR builder. Well, that should be easy. Because if we ask the IR builder to get insert block, hey, get insert block, that's what we need. And so here we can say that the else block is, oh wait, no. We have to do it after this point, though. Or no. Do we have to do it after that point? This gets confusing about where to do it. So, the else block is the initial part of an else, the top of it. And we generate the data inside of it, which may result in that. Or if we do need to save the insertion point. So we need to probably say auto pointer end of the else is the IR builder get insert block. We should do that to the same for the then of the end of the then. And then when that's done, they say if the end of the then is not terminated, and if the end of the else is not terminated, then we will set the insertion points to those blocks. Then here, when we merge, we'll set the insertion block, and we will set this to the end of the then and the end of the else. I will probably have to backport this onto the if statement to actually get a good result. Okay. Oh, we have something. Let's read our assembly output. Finish to 20. That's based on where it's coming from. That's based on where it's coming from. Okay, so if we do if expr and then I print out the status variable, 5, as expected. So now I can go back in and remove some print commands because there were some printings that I did in there. There. That's an unnecessary print. That's an unnecessary print. That's an unnecessary print. And that should be patched there. And then we get to say and then I will git add followed by a git diff. And then we will do a git commit. So we have here that okay. Implement backend implement type checking and Codegen for if expressions. And I will have to fix the formatting on that. So 1 second while I update the formatting here. There. So thank you for joining me. Hope you have a good day.